what you need to recall basically is this. So we had vectors, and we could write vectors in component form, which looks like this. All right, that was the vector in component form. Now, to find the magnitude of a vector, if you had it in component form, so for example, if AB is 0, 6, to find the magnitude of it, it was the first number 0 squared, right? So 0 squared plus the second number 6 squared, and that's how we found the magnitude of it in a square root. One other thing we're going to revisit is a unit vector. Remember how we found a unit vector? If this is the entire vector, the unit vector, which is this one in the black, it points in the same direction, but it's got a magnitude of 1, just 1. And the way we did that is we took the big vector and we just divided it by its magnitude. So if it was 6 units long, we divided it by 6, and now it's 1 unit long. Also, if we have a vector here, v, this vector v right here, remember we could resolve it into its components. We could resolve it into its vertical and horizontal components. So this is the horizontal component, and you have an angle theta here. So what's the cosine of theta? Well, it's this horizontal part x over v, right? So how much is x? X is v cosine theta. All right, so just to get us thinking about that stuff again. All right, so let's go on to section 3. We're talking about dot products and vector projections. All right, now, suppose you have two vectors, vector A in the blue, vector B in the green. All right, now suppose you had a flashlight and you shine a light onto vector A, but you have your flashlight, you're pointing the flashlight perpendicular to the green vector V, okay? You're gonna cast a shadow, right? A is gonna cast a shadow of itself onto the green one, is that right? There's gonna be a shadow of A on this surface B. If you were able to measure the length of that shadow, okay, that's a relevant quantity in here that we're going to talk about today. So if you shine a light, vector A casts a shadow here on vector B. All right? The length of that shadow, we don't call it a shadow in vector language, in the world of vectors, we call it a projection. So that's the projection of A onto B, right here. Projection of A onto B, and its abbreviation is like this. So projection of A onto B. Now, for fun, what we do is we take the length of that shadow, which, what are we calling it now? Not a shadow, but a projection. We take the length of that shadow, then we take the length of this green vector B, and we multiply them by each other. That is called a dot product. So a dot product is the product of the magnitude of the projection and the magnitude of B. All right, and we call that a dot product. So here's a question for you then. If the dot product, okay, if to find the dot product, we multiply the length of the shadow or the projection times the length of vector B, all right, to get the dot product. So here's a question. Is the dot product then going to be a vector or a scalar quantity? Is the length of the shadow vector or scalar? It's a length, so it's a scalar. A scalar is just a magnitude. A vector has a magnitude and a direction. What about the length of B? Is that a vector or a scalar quantity? Vector. That's also a scalar because it's just the length of B. So length is always scalar. So a scalar times a scalar, it's like 5 times 3 is another scalar number. Okay? So the dot product is always a scalar. Right, but what am I multiplying? I'm multiplying the length of B, just the length.
But if you weren't doing the length.
Right, but that wouldn't be a dot product. Because dot product is just length. Okay, now, that's what it is conceptually. It's actually a lot simpler mathematically than it is conceptually, because mathematically, how do we find A dot B? If you have A in component form, and if you have B in component form, then it's just A1, B1, A2, B2. So we just multiply the numbers by each other. Okay? Yeah. Question? No. Because it's the shadow. Remember, like your shadow is not always the same length as you, right? Depending on the angle that the flashlight is being held, the projection is going to be different lengths. Okay? All right, so look at what I have here. Let's see where the dot product comes from, first of all. Look at what we have here. This is the point of this lesson, is we're gonna find it throughout the whole chapter here. I'm sorry, the whole lesson. Okay, what kind of triangle is this? It's a right triangle, right? Okay, so if this is side A and this is side B and that's side C, how are they related? A squared plus B squared equals C squared, right? Whoops. But this is a vector, right? So it's A squared plus magnitude of B squared is equal to that squared. Is that right? This is Pythagorean theorem. A squared plus B squared equals C squared. Is that right?
That would make sense.
Okay. So now, let's just write all that down then.
Why do we use that absolute?
Because that magnitude. It means magnitude. The length of. Okay. Now, how did we find length of a vector? So if I have a vector AB, and suppose the components of AB are 3, 2, how did we find magnitude of it? Square root of 3 squared plus 2 squared. Now, if I have the endpoints in coordinate form, then it was this minus this squared, that minus that squared, remember? So the magnitude of AB is A1 minus B1 squared plus A2 minus B2 squared. This is just, section 2, okay? So now, for fun, I'm going to square this. And when I square, the square root goes away, right? Yeah. Okay. Now, just for fun, I'm going to distribute those squares. So it'll be A1 squared minus 2A1 B1 plus A2 squared minus 2A2 B2 plus B2 squared. Now, look at this. A1 squared plus A2 squared. I'm just going to write them next to each other. And I'm going to do the same for B1 squared plus B2 squared. And then minus 2 times, I'm going to factor it out, a1, b1 plus a2, b2. Okay? Now, okay, take a look at the red. a1 squared plus a2 squared. All right, so here I have my coordinates, my component form A, right? So that's just, so these two are just the length of A squared plus the length of B squared. Because if this is vector A, if this is vector A, then it's A1, A2 in component form. Yeah, and if I wanted to take the magnitude of it, it's A1 squared plus A2 squared. That's the magnitude. So this is just the length of A squared, the length of B squared, okay? Magnitude.
So why do you have to square it?
Well, because, look at this, right?
Yeah, but there has to be a reason. Yeah, why are we if we're proving this, then we can't.
No, we're not proving this.
How do we just get back to that? But I still don't understand why it's squared,
Because the magnitude would have been the square root of A squared plus B squared. It would have been the square root of A1 squared plus A2 squared, right? But this is without the square root, so it's the square of it. So it's the length of, okay, so minus 2 times A1 B1 plus A2 B2. Okay, you know what? Okay, so for time constraints, I'm going to leave this here and I'll revisit this. Let's move on and then we'll come back to this. Okay? No. So, okay, so orthogonal. Orthogonal vectors are perpendicular vectors. So basically, if you go to the orthodontist, they make your teeth straight. Right, that's what's an orthodontist. If you go to an orthopedic surgeon, they make your bones straight, right? So orthogonal, has to do with being straight. So they're perpendicular means, or orthogonal means perpendicular, okay? Now, okay. So you have two vectors here, vector A and vector B, right? Now, if I were to shine a light, remember, when I shine my light, my flashlight, it's always perpendicular to this, right? So if the flashlight is perpendicular to that, how much of the green's shadow will be cast on the red? None of it. If the shadow is 0, then so is the dot product, because the dot product is the shadow times something else. So if the angle between two vectors is 90 degrees, then the vectors are said to be orthogonal because the dot product will equal 0. Okay? So orthogonal vectors, dot product 0, it goes in both directions. Okay, so converse is true and so on. All right, let's find dot product here. All right, so u dot v is going to be, remember it's a scalar, so it's going to be negative 3 times 3 plus 4 times 6. Negative 9 plus 4 times 6 is 24. So u dot v is equal to 15. And that's all it is. It's just as straightforward as that. Yeah, it's a dot product. Remember, that's how we write it, u dot v. Here, u dot v is 2 times negative 14 plus 7 times 4, negative 28 plus 28. So u dot v is 0. What does that mean about the vectors? They're orthogonal.
Would you
No, you just know. Sometimes you'll be asked, are they orthogonal? Okay. Now, okay, so the vectors follow some of the same properties as do scalars. For example, commutative property, right? U dot V and V dot U are the same. Distributive property applies. Multiplying by a scalar, you can multiply any which way. If you have a vector that's 0, 0, dot another vector, you just get 0. Now, what if you have a dot product of the same vector with itself? So suppose vector A is 3, 4. And now you want to do A dot A. What do you get? You get 3 times 3 plus 4 times 4. What is that? 3 squared plus 4 squared. What is that the same as? It's the magnitude. It's the square of the magnitude. All right? So A dot A is the length times itself. So A dot A is the magnitude squared. Therefore, the magnitude, right? The dot product can be used to find magnitude. Okay, what do I mean by that? So here it says, use the dot product to find the magnitude of A. All right, so let's do that. So magnitude of A is the square root of A dot A. So this is the square root of -6 times -6 plus 5 times 5. And at the end of the day, that's just the square root of 61. Okay? Why does that work? Because if you have a vector A, and now you're doing A dot A, and you reproduce the same vector A here, and if you shine your light on it, how much of A's shadow is cast on A? All of it, right? So that's why like it just multiplies by itself. And remember, dot product was the length of the bottom one times the shadow of the top one. So it's just the same thing by itself. You'll see. Yeah. Okay. So how would I find now the angle between two vectors? Okay. All right. So here you have the two vectors like we said before. This here is the projection, and you have an angle theta in between. All right. Now, let's talk about what A dot B is, right? Remember what we said, that this was just the length of the shadow of A times the length of B. Okay, now the shadow is this much. All right, how big is that in terms of like the angle? So that red X, right, cosine of theta is X over magnitude of A. Is that right? Yes, in that right triangle. So then X is A cosine theta, right? So this is A. Okay, right triangles. This is an angle theta. Cosine of the angle theta is adjacent over hypotenuse. So X over A. So cosine is X over A. Multiply both sides by A. I get A cosine theta. Well, because it's the length, right? Cosine is a length over a length. Okay. So, what did we say A dot B was? We said A dot B is the length of the shadow, which is the red part. So it's A cosine theta times the length of B. Okay? And now, just writing them, like just rearranging them, A dot B is equal to length of A, length of B, cosine of theta. Okay? So now, do we know what cosine of theta is? Can I solve the one in the box for cosine of theta? You just divide. It would be A dot B over magnitude of A, magnitude of B. Okay? So that is this formula here, which we just came up with all on our own. Okay? The two things in the boxes are exactly the same thing. I wrote this based on my definition of dot product. It's the same as this.
No, he's saying the top half is the numerator is the same as the denominator. Yes.
Okay, so I took this. Okay, listen. I took this, and now I said, okay, what's cosine of theta? Solve this for cosine of theta. So divide, and that turns to that.
I understand that.
Right.
The numerator is the same as the denominator.
The numerator is A dot B, which is a quantity on its own, A dot B. That's how this is A dot B here. And the denominator is magnitude of A, they're not the same. Let's do this example and you'll see, okay? So here we need to find the angle theta. So what do we need for this? I need A dot B, okay? So let's find A dot B. A dot B, so the formula is cosine of theta is A dot B over magnitude of A, magnitude of B. So what's A dot B? Sorry, in this case, they're all using V's. So let me adjust this for, just rewrite it. Okay, so U dot V is 1 times 2 plus negative 4 times 6. So U dot V is equal to negative 22. All right, now, magnitude of U is the square root of 1 squared plus 4 squared. So magnitude of U is the square root of 17. Magnitude of V is the square root of 2 squared plus 6 squared, which is the square root of 40, and I'm going to be rebellious and just leave it that way, not simplify it. Now, cosine of theta is U dot V, which is negative 22. So you see how they're each different quantities? Like I see U dot V, and to me that's one thing. That's a thing. Magnitude of U is root 17. Magnitude of V is root 40. Now, so theta is inverse cosine negative 22 over the square root of 17 times 40. Let's plug that in, people. We're going to be in degree mode. So theta is 147.5 degrees. It's got to be in degree mode. Okay? All right. What have we found? So take a look at vector U. It's at 1 comma negative 4 here. That's vector U. Vector V is 2 and 6. That's vector V. All right. And what we just found is that that angle is 147.5 degrees. Okay? No, that's section 1. I know, that's section 1. Okay, projection. Let's talk about projection. Okay. So we've been saying that this projection is the length of the shadow, which is a scalar, right? Now, how did we find the projection? It was A dot B over B, right? That's what we did here. Okay? All right, now, this is just the magnitude. Okay, this is the magnitude. This gives you a length. The projection is a length. All right? Now, how do I get it to be in the same direction as what I want it to be in? So if I just have a length, how do I give it a direction and turn it into a vector, right? In order for me to give something a direction, I need to multiply it by a unit vector. Do you remember what unit vectors were? We were just talking about it right now. So a unit vector has a magnitude of 1, but it's got a specific direction. So I can take any number, like 3, multiply that by this unit vector, and now it'll be a vector of 3 units that, that points in that direction, okay? So what we're going to do here is we're going to take the projection and multiply it by the unit vector of B. So if I have a vector B, right, what's the unit vector? Well, we take the magnitude of B and, right, so it's the vector B, and then we take the magnitude of B and we divide it. So that's the unit vector for B. So now what we're going to do is we're going to take the projection, the length of the projection, so the one in the green circle is just the length, and we're going to multiply it by the unit vector. Okay, so that gives it direction. Now, if we just clean it up a little bit, it's A dot B over this magnitude squared times the vector B. So let's just write it like this. It's A dot B over the magnitude of B squared times B vector. Okay, so that's the projection. That's the shadow, and now with a direction in the same direction as B. All right, so let's find the projection of this thing. All right, so first I need U dot V, which is -1 times 4 plus 5 times 6, 26. I need magnitude of V, 16 plus 36. So magnitude of V is √52. All right, and I just leave it like that because what I really need is magnitude of V squared, so it's just 52. Okay. Yeah, so now I need the projection. Well, the formula doesn't call for it. So the projection of U onto V is U dot V over the magnitude of V squared times vector V. Okay? So, what's U dot V? 26. Over the magnitude of V squared is 52. Times, what's the vector V? It's 4, 6. Right, the magnitude of V was root 52. The square of that was just 52. So the projection of U over V is 1/2 4,6 2, 3. Okay? All right.
Do you do it if they wrote it differently and projection of beyond you?
Yeah, then it would all be flipped. Okay. For fun, because, you know, this is like a newborn now, this is a new vector that we found, we're going to give it a name. We're going to call it vector W. UVW. Okay? Now, so that's the projection that we're talking about. Now look at this thing. It says write U as the sum of two orthogonal vectors, one of which is the projection of U onto V. Oh my. Okay. We're going to write U as the sum of two vectors. Let's just ignore the word orthogonal for a minute. Of two vectors, one of which is the projection of U onto V. Which vector is that? U, V, or W? That's W. So what I want is U, vector U, to be the sum of two orthogonal vectors, one of which is W. So W plus some other vector, I don't know, let's just call that Z. Okay? All right? So it just says to write U as the sum of two random vectors, but you want one of them to be that W vector. Well, right, it has to be orthogonal. Let's keep the orthogonal for later. So it just says to write this vector U as the sum of two other vectors. One of them is W. Now, do I have U? I have U. Do I have W? Yeah. Do I have Z? No. Can I solve for Z though? Can I just rearrange this for Z? It's U minus W, right? So Z is U, which is -1,5 minus 2,3. So Z -3,2. Now, what does this say? It says to write U as the sum of W plus Z. What's U? -1,5. That's equal to W plus what? Okay. What about that word orthogonal? Okay, you know what? For fun, can you find the dot product of those two, please? Let's find the dot product. Oh my gosh. It's 0. So what do we know about those two vectors then? They're orthogonal. You tell me. 2 times -3 and 2 times +3. Right? So it's -6 plus 6, which is 0. So the dot product is 2 times -3 plus 3 times 2, so those two are orthogonal.
With the information that we got.
Stuff. So the dot product stuff, right? Here's how it's used. What's the formula for work? Force. Work equals force times distance. Work equals force times distance, but not all of your force is applied towards the work that you do. So you have to, so the part of the force, or let me say it this way. In order for you to be doing work, the force needs to be applied in the same direction as the motion. So if you're pushing a box, if you want to push a box horizontally, then the force needs to be applied horizontally in order for you to be doing work. Okay? If the force and the motion are not in the same direction, there is no work. You can push on something until you're blue in the face and you've got perspiration, but if there is no motion, then there is zero work being done. Okay? So, work, yeah, it's sort of force times distance. Work is sort of force times distance. In actuality, work is a scalar quantity. Work is not force times distance. Work is force dot distance. It's F dot D. Okay? It's F dot D. That means only the direction of the force that's applied in the same direction as the motion will be applied towards the work. So, a person pushes a box with constant force of 40 newtons at a constant angle of 45 degrees. So here there is an angle of 45 degrees. Find the work done in joules to move the box 12 meters. So joules is Newton times meter. All right. Now, okay, the formula, I will give you the formula, but you need to do the rest. So now, let's see about the force here. This is the force vector. And it's 40 newtons. Now, there is a vertical component and there is a horizontal component. Okay? This angle is 45 degrees. The horizontal component happens to be adjacent to the angle, so it's cosine. So this is 40 cosine 45. This is 40 sine 45. All right, now, what about the distance vector? The distance vector, it says that the distance is moved, is 12 meters, and I guess it's implied. It's implied that the box moves 12 meters horizontally. It should have stated, I should have stated, but we'll add it here, horizontally. Okay, so what's the D vector in component form then, if it moves 12 meters horizontally? 12 comma 0. Now, work is F dot D. Okay? F dot D. Okay, so what was the force vector? Let's write the force vector here. It's 40 cosine 45. 40 sine 45. So the work vector is 40 cosine 45. I'm sorry, work is not a vector. Work is 40 cosine 45 times 12 plus 40 sine 45 times 0. So do you see what that does? Is because there is no motion in the y direction, it cancels out all the force being applied in the y direction. So the part of the force that's being applied vertically, as in your force vector, it's just going to waste. It's not doing any work. It's not contributing to the work that you're doing. So the work is just 339.4 joules. Okay, I know. All right. So let's draw some of this stuff that we were talking about. So let's draw some of the stuff that we're talking about. So, okay. All right, so listen up here. Okay, here's what we're doing. So, I have, okay, so I'm gonna go back to example 4. Remember example 4? We had in example 4 two vectors here. Example 5, I guess. Sorry, example 5. All right. We have two vectors, -1, 5, and 4 and 6. So I'm going to draw those here. So it's -1, 5. -1, 5. 1, 2, 3, 4, 5. Is that 5? Okay, so that's the u vector. That shouldn't have an arrow in the bottom, but it's okay. So let's do a v vector. V is 4, 6. 1, 2, 3, 4, 5, 6. All right. Now, what about the projection? The projection was 2, 3, right? So let's take a look at the projection. What color do we do for the projection? Blue, eh? So what is it? It's 2, 3. 1, 2, 1, 2, 3. Look at that. Oh my God. So if we were then to shine a light here, perpendicular to that, okay, the shadow of this would be that. Okay, that is pretty cool. So it has to be perpendicular to this, like this, and the shadow would be just like that. So that's vector W right there. Okay. Now, what was the other vector that we found? Vector Z. What color? Let's see. We'll make that pink. Let's do pink.
Wait,
I haven't done.
Rose. Go down. Let's do rose.
I think that's rose. So -3, 2. 1, 2, 3. 1, 2. Okay, check it out. Check it out. This is vector Z. This is vector Z. Now look. Hey, shh. This is vector Z. What did we say W dot Z was? W dot Z, it was 0, right? So what's the angle then in between W and Z? 90 degrees. So W and Z are orthogonal. Okay? Not only that, oh my God, look, oh my God, that's, okay, wait, this is what I was gonna do, So remember how we said, what is it? Oh my God, hang on, oh my God, okay, so U, okay, watch. Remember how we said U was equal to W plus Z? Okay, watch. I need my mouse for this. Hang on. Hang on. Look. W plus Z. So this is W. If I take Z and add my vectors, watch. Oh, okay, so look at that. W plus Z is equal to U. And this is a 90-degree angle here. This is a 90-degree angle here. Isn't that cool? That's what we did. Okay, so this homework is due tomorrow. Oh my gosh. Okay.